All right, dear. Very good evening, everyone. Welcome back to OM Institute and welcome back to the GATE 2025 Champion Series. And this is control systems, some important topics we are discussing. So last session on Monday, we discussed the controllability and observability concept along with the basic and the generic test that is known as the Kalman's test. Okay. Another test for specific forms, but very important, especially if the state space model is given in the DCF or the JCF form. This is actually very helpful for you. So last session on Monday we discussed. All right. So I think for me the audio and video looks good. You can also check it out. If there is any problem, do mention me. But yeah, looks fine. All looks fine. Okay, very good evening, everyone. Good evening, Chandan Kumar. Okay. So now the special test, especially for the DCF and the JCF form, very simplified. There also you can apply Kalman's test. Okay, but Gilbert's test will give you results in seconds. Okay, if it is DCF or JCF state space model given to you. So what is that Gilbert's test? Let us learn in this today's session. Okay, right. So guys, as I told you, the big time update is GATE 2025 exam is coming closer and closer. And yes, for the upcoming GATE 2025, the OM Institute brings to you the All India Mega Free Online Mock Test. Yes, guys, just feel the GATE before GATE. Yes, see actual how much do you perform. Okay, actually how much do you perform? Okay, among thousands and thousands of aspirants appearing for the GATE examination. So this free mega online mock test exactly as per the GATE pattern, 3 hours, 65 questions on online pattern. Okay, because since GATE is online, so on 12th of January 2025, 2:30 p.m. to 5:30 p.m. this examination is going to be conducted, and also there are special exciting gifts for the top 5 students, top 5 performance. Okay, they will be all India ranking so that you can assess your performance, how you are going. Okay, real-time experience of the exam and detailed question explanation for all the questions, all the 65 questions. Okay, so the registration is free. Just to register, you can also visit our website or directly scan this QR code. That makes it very simple. Okay, just scan this QR code and it will take few seconds. You can just register for this free mega mock test. For any more details, you can call upon 95156 94053. Okay. Also, guys, the big time next update is for GATE 2026 for EE and EC branch, the first offline regular batch. Okay, for GATE 2026 starts from February 24th. Starts from February 24th. Okay, and yes, if there is an early bird discount, if you register before 30th of Jan, you get 4,000 additional discount. The fee 65,999 is already currently priced as 54,999, and you will get additional 4,000 discount over it. And also, some special discounts for specific category of students that is definitely mentioned here. Okay, now guys, let's talk about quick review. This is highlights, okay, of what we were discussing. Okay, let's start with that highlights first of all. Okay, so state space model. So the previous session was not entirely on state space analysis. State space analysis, of course, is a big topic. Controllability and observability is an important topic, and many students were asking. So that is why I took a special session on controllability, observability. We covered Kalman's test in the last one. That is the most generic test, but a special test, Gilbert's test, we are going to take today. So we started with a state space model which has state equation and output equation. State equation is x dot equal to ax plus bu. Output equation y equal to cx plus du. Then I explained you what is controllability, observability concept, and then I straight away went to the Kalman's controllability test. Okay, which says that a system is controllable if the controllability matrix has rank n, and this is the controllability matrix. Kalman's test is important because that is the most generic test, and if you by chance miss the video, you can just go to the previous video 2 days back, Monday, same channel. You can find it up. Okay, and always better be subscribed to the channel so that any sessions that are coming up, you are already notified and you can watch it without a miss. Okay, right. So if you feel that the content of the channel is beneficial, you can subscribe it immediately. Okay, we'll plan sessions on all other subjects, analog as well, Bhushan, and don't worry, very soon the complete revision marathons. We will very soon announce it, but for the complete revision marathons are also going to come up on the YouTube channel. Okay, so the controllability matrix should have rank n, and then if it is specifically SISO, if it is specifically single input, single output, okay, for the, rank n, we just came up to the final conclusion that determinant of s not equal to 0, and hence the problem becomes simple. Okay, and then I told you the observability test of Kalman's, okay, which says that a system is observable if the observability matrix mentioned here will have the rank n. And again, once we convert this to the SISO model, we came to a simple conclusion that mod v not equal to 0. If this observability matrix is non-singular, okay, system is going to be observable. Okay, now we solved some basic problems on the Kalman's test. Okay, and after solving few problems, we came up to special conclusions, like whenever your system is given in the CCF form, CCF, controllable canonical form, it is always controllable. That is how the name comes up, controllable canonical form. It is always controllable, and then we came up with a shortcut for observability. If there is no pole zero cancellation in the transfer function, the system will be observable. Another question I took, which was CCF model only, system is controllable. Okay, but once I find a transfer function, okay, there is a pole zero cancellation. So if there is a pole zero cancellation, system is not observable. Okay, don't worry if you missed it, you can go and watch it in the previous session, because anyways, you will not be troubled with today's session, because that is about DCF and JCF form. Okay, right. So these were some of the shortcuts, and then I also made a review. Okay, I also made a review of the standard state space models. 4 standard state space model. You must generally know, very important, not only for controllability, observability, even for other topics of state space analysis. These 4 forms must be very clearly known to you. CCF, controllable canonical form. OCF, observable canonical form. Normal forms. Okay, there are 2 normal forms that we are going to take today. Okay, DCF, the diagonal canonical form, JCF, the Jordan's canonical form. In the previous session, I also told you then what CCF form looks like. Okay, a review of the state space model was taken. Basic revision was done around that. Okay, like if it is a second order system, how the CCF form, how do you remember, how do you write the CCF form? And if you remember CCF, how do you quickly write OCF also? We also talked about third order, and we generalized that even if it is higher order also, how do you write down the CCF form? How do you write down the CCF form? Now, dear, this was done. This is the quick highlights. Now, let us go to the normal forms, because the Gilbert's test that we are covering today is especially for the normal forms. Especially for the normal forms. Okay, it is especially for the normal form. Okay, now the first normal form is the DCF. Let us start here. Let me first review how a DCF model looks like, and then I will tell you the Gilbert's test, because see, there are 2 Gilbert's tests. Okay, there are 2 Gilbert's tests. One is for the DCF and one is for the JCF. Okay, one is for the DCF, one is for the JCF. Okay, but what is that Gilbert's test? Controllability observability, very simple. Okay, I'll make this language very, very simple for you. Okay, but let's understand. Okay, what DCF form? Let's have a review in case if you have not attended what a DCF state space model looks like. Okay, suppose I've started with a third order example. I will tell you for second order also, no worries. Okay, I have started with a third order basically, not the second order, sorry. Okay, I have started with the third order transfer function. As you can see, the denominator is cubic one. Okay, it starts with s cube. Okay, so we have b into c2 s square plus c1s plus c0 upon s cube plus a2 s square plus a1s plus a0. Same third order system you can also express in the CCF model, which is done. And now, what is the DCF model? Now, dear, first of all, in this we try to factorize the denominator. It's a cubic denominator, and hence it will have 3 factors. Suppose the 3 factors are s plus p1, s plus p2, s plus p3. Okay, and then we split it into partial fraction. Okay, with the condition here that p1, p2, p3 are all distinct. If they are same, what will happen? That you will come to know in the Jordan's form. Okay, so the procedure is factorize the denominator. Maybe it has 3 roots, s plus p1, s plus p2, s plus p3. These are the 3 factors, and then I split it into partial fraction. Suppose after splitting into partial fractions, we get some number k1 upon s plus p1, k2 upon s plus p2, and k3 upon s plus p3. Okay, then the DCF form is written as x dot equal to ax plus bu. We know what is the state space model. X dot is ax plus bu, y equal to the cx. Okay, so x dot is ax plus bu. What is the A matrix? A matrix will only be a diagonal matrix. That is how the name comes, DCF, diagonal canonical form, where the system matrix A will be a diagonal matrix. diagonal matrix containing the diagonal elements which are just equal to the poles of the control system. Right? Diagonal matrix, okay, with diagonal entries equal to, with diagonal entries or eigenvalues equal to, eigenvalues equal to the poles. What are the poles here? Okay, what are the poles? Okay, so if you calculate the poles, S equal to minus P1, minus P2, minus P3. Okay, minus P1, minus P2, minus P3. Okay, so these are the diagonal entries, rest are 0. So you get a diagonal matrix with all the diagonal elements equal to the poles, or for a diagonal matrix, diagonal elements also represent the eigenvalues directly. So all the diagonal elements or eigenvalues are equal to the poles of the control system plus some matrix B indent into U and Y equal to Cx. Okay, so this is what is your A matrix, this is your B matrix, and this is your C matrix. Now, what is B and C matrix? Okay, what is this L1, M1, N1 and L2, M2, N2? More with questions I will elaborate. Okay, so it should be such that L1 into L2 should be K1, the partial fraction coefficient K1. M1 into M2, the product of second to second term should be equal to second partial fraction coefficient K2, and the product N1 into N2, the product of the third to third element of the BC matrix, B and C matrix, should be equal to the K3. Okay, even if I take, even if I want to take a second order example, okay, even if I want to take a second order, then we will go to JCF, just wait a second. Okay, so if I even write it in the second order form, see, second order, what is the transfer function? Second order means some quadratic denominator, maybe some S square plus A1S plus A naught, and B numerator C1S plus C naught. Okay. Now to write in the DCF form, what I am telling you, to write in the DCF form, what you first need to do is you need to factorize the denominator. Okay, you need to factorize the denominator. Okay, suppose I factorize the denominator and I get the two factors as S plus P1, S plus P2. And what is the next thing you have to do? You have to split into partial fraction. Suppose you split into partial fraction and you get, okay, K1 upon S plus P1, okay, plus K2, some K1, K2 you can obtain. Okay, so after splitting into partial fraction, suppose you get this form. Okay, K1 upon S plus P1 plus K2 upon S plus P2, correct? Now, what is the DCF form for this? What is the DCF state space model for this? I will write down x dot equal to AX plus BU, second order system, the 2 cross 2 matrix, x dot equal to AX plus BU and Y equal to CX. That is what you have to write down. Now, what is the A matrix I told you? DCF, diagonal canonical form, means A will be a diagonal matrix. Meaning that A will be a diagonal matrix with the diagonal entries equal to the poles. What are the poles? When you solve for the poles, minus P1 and minus P2. All others are 0. Okay, plus BU. What is B? Suppose this is L1, M1. And what is Y equal to CX? Suppose this is L2, M2. Correct. Then I told you the product of first to first element, okay, the product of first to first element L1, L2, okay, should be equal to K1, and the product of second to second M1, M2 should be equal to K2. Okay, should be equal to K2, right? Suppose, okay, just take an example for understanding. Okay, suppose if I give you an example of the kind, suppose a simple transfer function, 1 upon S square plus 3S plus 2, something like that is given. 1 upon S square plus 3S plus 2, correct? 1 upon S square plus 3S plus 2. Okay, so what are the factors of it? S square plus 3S plus 2. Simple, S plus 1, S plus 2. Simple it is, S plus 1, S plus 2. Okay, and now to split into partial, it is a simple case. I will directly split into partial fraction. Actually, it will just be a subtraction. 1 upon S plus 1 minus 1 upon S plus 2. 1 upon S plus 1 minus 1 upon S plus 2. When you solve, S plus 2 minus S plus 1 will be 1. Okay. The Y by U is 1 upon S plus 1. Let me write it in the plus form. The plus minus 1 upon S plus 2. Okay, better do it this way. Better do it this way. Now, if this is Y by U, okay, now see, what is the state space form? What are the poles? Minus 1, minus 2. The x dot equal to AX plus BU. What is the A matrix? A matrix, diagonal matrix containing the poles. Poles are -1 and -2. Okay, and y equal to Cx. Now here normally we write down L1 and M1, L2, M2. But what should be simple thing is, okay, here suppose you write down L2. So what should be the product of this L1 and L2? Okay, the product of this L1, L2. The product of this L1, L2 should be equal to K1. And what is the first partial fraction coefficient? K1 is 1. So L1 into L2 should be 1. L1 into L2 is 1. So you can take both of them 1, 1. And then next what I told you, next element that is coming up is M1, M2. The product of second to second term should be K2. Okay, M1, M2 should be K2. And what is the K2? -1. Okay, the product of them is -1. Correct? Now -1 means, okay, -1 means a plus and a minus. One of them plus, one of them minus. Anyone, suppose you take here 1, you can take here -1 or vice versa. If you take minus here, you can take plus here, anything. The product of them should be negative. That is what is the M1, M2 is K2, which is -1. Okay, so 1 and -1, you can take it like this, okay? Right, dear? This is what it is. Done. Okay, this is what you must know. Okay, now, what is the JCF form? What is the JCF form? Now, similar process. Suppose I again start with the third order example. Okay, and then let me just explain you JCF also, and then I will start the Gilbert's test. Some basic state space models I'm just revising right now. Okay, so again, suppose you are given a third order transfer function. The first step, okay, is factorizing it. But now sometimes what happens, that factors are repeated. See, what I told you very clearly in the previous example, P1, P2, P3. Or let me put it this way. Okay, what I started normally, poles are, in the first case, poles are -P1, -P2, -P3, all distinct. That means all poles or all diagonal elements are distinct here. Clear? Okay, now again, suppose you got a third order transfer function, you factorize it. Whether it will fit into DCF or JCF, you factorize it. Okay, after factorization, what are the poles you get here? The poles are, see, s plus p1 whole square into s plus p2. The poles are -P1, -P2. Okay, repeated pole condition. Okay. Earlier case, DCF is applicable if all poles are distinct or unique. But here there is the repeated pole. Okay, so we have the factorized denominator as s plus p1 whole square into s plus p2. Correct, dear? Okay, now we split into partial fraction. And whenever we split into partial fraction, corresponding to the repeated factor, corresponding to the second order term in the denominator, in the partial fraction method, we always have two terms. One is k upon s plus p whole square. One is k upon s plus p. It's second order version and the first order version. So we write it as k1 upon s plus p1 whole square plus k2 upon s plus p1 plus k3 upon s plus p3. Okay, now what is the state space form? What is the JCF state space form? X dot is ax plus bu, y equal to cx. Okay, now see, what is cx? Here no product of b and c element, simple. What is the C matrix? Directly partial fraction numbers k1, k2, k3. Okay, the C matrix is directly the partial fraction numbers. Okay, that is K1, K2, K3. Okay, K1, K2, K3. That's it. Directly the partial fraction numbers. Okay, dear? That is the C matrix. The B matrix has fixed element 0, 1, 1. The B matrix has the fixed element 0, 1, 1. Okay, and X dot equal to AX. What is the A matrix? Okay, the A matrix here will be a upper triangular matrix. Okay, upper triangular matrix with the diagonal. See, this is the upper triangle. Na? All the elements are fitted in the upper triangle. There is nothing below the diagonal element. There is nothing in the lower triangle. Right? Yes. Good evening, Raj. Good evening, Hari Pavan. Okay. So that is what it is, the upper triangular matrix. And in that upper triangular matrix, what are the diagonal numbers? Again, the diagonal entries or the eigenvalues are equal to the poles -P1, -P1, repeated pole, and then the another pole -P2, -P1, -P1, and then the another pole, that is the -P2. Okay, above the repeated pole, this is the repeated pole, above the repeated pole it will be 1. This is the way to remember actually. Okay, so diagonal elements are poles. What are the poles? Minus P1, minus P1, minus P2. And above the repeated pole, this one is the repeated, na? Already I've written one minus P1, another repeated. Above the repeated pole, it has to be having 1. It has to be having what? 1. That is what it is, okay? This is what is JCF form. Even it can be there for second order also. Okay, even it can be there for second order also. Let me write down for second order. Okay, suppose second order transfer function again given in some form BC1S plus C0 divided by S square plus A1S plus A0. But whether it is DCF or JCF, we need to factorize. In the CCF and OCF, we don't talk about the factorization. Okay, so now this is equal to, okay, suppose you try to factorize the denominator, but you get only a repeated factor. Suppose S plus P1, quadratic na? So 2 poles, but both are repeated only. S plus P1 whole square. Suppose you write it as S plus P1 whole square, correct? S plus P1 whole square. Now, we will split into partial fraction, and suppose after splitting into partial fraction, we get the form K1 upon S plus P1 whole square plus some constant K2 upon S plus P1. Okay, suppose this is what I get. Okay. Now, what is the JCF answer? What is the JCF state space model? X dot is equal to AX. This time A will be a 2 cross 2 matrix. Okay, 2 cross 2 upper triangular matrix. What will be the diagonal elements? Diagonal elements will be the poles. Okay, poles means minus P1, only repeated. JCF form is applicable for repeated poles only. Minus P1. And what I told you, above the repeated pole, write down 1. Okay. Plus BU. B 0, 1. Fixed element. First 0 and rest will be 1. And Y equal to CX. What is the C matrix here? I told you, simply partial fraction numbers. K1, K2. Okay, K1, K2. Like the previous one was containing K1, K2, K3. Okay, here it will just contain K1, K2. That's it. Okay. Now let's come to the Gilbert's test first for the DCF and then for the JCF, one by one. Okay, what is the Gilbert's test for the DCF? Entire row. Now guys, I'm actually starting the content of today's class. It was a basic review of DCF and JCF. Okay. So Gilbert's test. What is the Gilbert's controllability test? Have a look into this one first. Entire row of B matrix. That correspond to distinct eigenvalues should not have all 0 elements. I will explain you simply. Okay. Observability test. Entire column of C matrix that corresponds to distinct eigenvalues should not have all 0 elements. Now let's understand. Okay, by example, it will be easy. Okay, consider the state space model and there are the 4 options, and dear, these are normally 2 marks question. Again, I repeat, you can still apply Kalman's onto it. But if you identify the special normal forms, Kalman's, you don't have to think, that will take time. See, what type of matrix is given to you? A diagonal matrix. See, what is the identification of a DCF form? DCF form should contain matrix A as a diagonal matrix with all distinct diagonal elements, with all distinct poles. Okay, right. So what is this, dear? This is the way to identify. Yes, there is a diagonal matrix. Okay, yes, there is a diagonal matrix. With what? Okay, with distinct diagonal elements or distinct eigenvalues. Because as I told you, for a diagonal matrix, eigenvalues are equal to the diagonal elements only. So there is a diagonal matrix with distinct eigenvalues, and that is what is DCF. That is what is DCF. DCF means 2 things you have to confirm. Is it diagonal matrix? Okay. Are there distinct elements? Okay. Then only it is DCF. Repeated also factor should not be there. Okay. Now, is it controllable, observable? What is the condition? Kalman's will definitely take time. Now, let us come. I've taken this matrix once again. It is a DCF question, clear? And now, let us first apply the controllability test here, one by one. Let us apply the controllability test here. See here, what do I say in controllability? Entire row of B matrix corresponding to distinct eigenvalues should not have all 0 elements. Should not have all 0 elements. Okay, the entire row should not be 0. That's what I mean. Which entire row? of a B matrix corresponding to distinct eigenvalues. Okay, so how many distinct eigenvalues? 1, 2, 3. All three are distinct only. That is why it is a diagonal DCF form. Okay, so there are 3 distinct eigenvalues. Okay, corresponding to every eigenvalue, corresponding to every distinct eigenvalue, go to every row of the B matrix. Go to every row of the B matrix. So first eigenvalue, go to the first row of B. Correspondingly, first eigenvalue, first diagonal element, go to the first row of the B matrix. Okay, is it a row of 0? Is it a row of 0? See, I will use the word ROZ to represent row of 0. See, here this row contains only one element. Still, why do I call it as a row? Because sometimes MIMO, okay, if it is MIMO system, multiple input, multiple output, there can be more elements within the row. What you should see is that there should be no row of 0. Okay, so is it row of 0? No, I will call it as, I will use a short form NZR. What is NZR? I will use a short form here, non-zero row. What is NZR? Is this a row of 0? No, it is NZR. Okay. Now you have to check this for every diagonal element. Okay. Now this is the second diagonal element. This is known as the second distinct eigenvalue. Corresponding to the second eigenvalue, I will go to the second row. I will go to the second row of the B matrix, and here also I find that it is a non-zero row. Okay. Okay. Corresponding to the third eigenvalue, we go to the third row of B, and third row contains only 0. It is a ROZ. This is known as the row of 0. And corresponding, see what I told you, entire of B matrix corresponding to distinct eigenvalue should not have all 0 elements. Okay. And if you get a row of 0, then the system is not controllable. Controllability failed here. Controllability failed here. Even if you get this one row of 0, the system is not controllable. The system is not controllable. Everybody clear? System is not controllable. System is going to be not controllable. Fine. Let's have a look into it. System will be uncontrollable. Okay. In fact, you can also say which state is uncontrollable. So, which row is 0? The third row is 0. We can Gilbert's test. That is the benefit. In Gilbert's test, you can also say if a system is uncontrollable, which state variable specifically is uncontrollable. So, I can say that, okay, state variable. Which state variable? Third one. Because third one was a row of 0. The state variable x3 is uncontrollable. That also, is one of the benefit of Gilbert's test. You can directly look and say which particular state variable is uncontrollable. Okay. Okay, Likita, we'll plan other sessions also. All right. Let's move ahead to the next. Right now, this is only controllability. Now, dear, let us go to the observability. Okay. Same data I have taken here, explaining you observability separately. Explaining you this observability separately. Now, what do I need for observability? Come to the observability test. Entire column of C matrix. Entire column of C matrix that corresponds to distinct eigenvalues. Entire column of C matrix that corresponds to distinct eigenvalues should not have all 0 elements. Now I need to go to the columns of C matrix corresponding to distinct eigenvalues. Okay, this is done. Now come here. How many distinct eigenvalues? Again, dear, 3 distinct eigenvalues. Again, dear, 3 distinct eigenvalues. -1, -2, -3. Corresponding to every eigenvalue, you go to column of C. Okay, now again I will use the notation COZ. Like ROZ, I will use here the word COZ. COZ means column of zeros. And similarly, I will use another short form here, NZC. What is NZC? Non-zero column. Non-zero column. Now, corresponding to every diagonal element, every eigenvalue, you will go to every column of C. So, first eigenvalue, first column of C. Here, B matrix is not required. Okay, now come here. Every diagonal element corresponds to every column. Now, I go to first column, whether it is a 0 or non-zero. Yes, this is non-zero column. Good, I need non-zero only. Second eigenvalue, go to the second column of C, and this is column of zeros. It contains only zeros. And even if you get one column of 0, you can stop your problem here. Okay, the system is unobservable. Finish. The system is unobservable. The system is unobservable. Okay, but yeah, even if I go to third, no problem. Question can stop here. It is unobservable. If I go to the third, now you see, third diagonal element means third column, and third column is non-zero. But no problem. Any one column zero, na? COZ means unobservable. Again, I told you the beauty of Gilbert's test is you can even say which state is not observable. Okay, so which column? Second column is 0, and I can say that the state variable x2 the state variable x2 is unobservable. The state variable x2 is unobservable, right? The state variable x2 is unobservable. The state variable x2 is unobservable. Correct? That is what it is. Okay, let's go ahead to the next. Now, dear, before I go to the next problem, let us summarize actually. Okay, why this was unobservable? The third row was 0. Dear, if here also non-zero was there, then this will be completely controllable. Similarly, here also, if this was non-zero, this will be observable also completely. So, before I take up the next problem, what can I define for you? See, direct result, a 3 cross 3, if you want controllable as well as observable form, controllable and observable DCF form. Okay, how it should look like. Okay, now DCF, diagonal canonical form. Diagonal matrix with distinct roots, minus P1, minus P2, minus P3. Minus P1, minus P2, minus 3. X dot equal to AX. Okay, plus BU, and Y is equal to CX. Y is equal to CX. Y is equal to the CX. Okay, now see, as I told you, why the system became uncontrollable? Because this was 0. If this was also non-zero, that means if you want complete controllable system, okay, this element should be non-zero, second also non-zero, third also non-zero. Okay, this confirms controllability. And if you want the observable system also, all the 3 columns here also it should contain non-zero element, here also non-zero, here also non-zero. If you have any such, if you have this form, it will be observable. Okay, now the questions will more or less become a visual question for you. I will show you how. Now the question will just become a visual question for you. Have a look into this question. I'll take another question on DCF. Just a second. Where is that? Okay, I have a 2 cross 2 question. No problem. I will write down another question for you. No worries. I will write down. Suppose the state space model has been given to you. Tell me whether the system is controllable, observable. What is my comment for the last question? Last question, it was uncontrollable. I'll tick mark the option. It was uncontrollable and unobservable. Okay, so option number C for the last question. It was not controllable also. It was not observable also. Now I have written you another question. Now I have written for you another question. Now see here very clearly. 1, 2, 3, all are non-zero. All are non-zero. By looking into the matrix, I will say system is controllable. I'm telling you, it will become a visual question. Observe and say. Okay. Then C matrix for observability. This one is 0. This one is 0. Okay, so unobservable. Anyone 0, it is not observable. So answer for the question, it is controllable but unobservable. Okay, here also non-zero, the controllable and observable both. For controllability, just focus on the B matrix. For observability, focus on the C matrix. Finish. Okay, these are, I'm telling you, commonly 2 marks question. You can finish in seconds. If it is a second order question, So like this was a 2 cross 2 form, na? Okay, similarly dear, if I am about to tell you, if I tell you what is a 2 cross 2 condition also, similar condition dear, 2 cross 2 controllable and observable DCF form, 2 cross 2 controllable and observable DCF form, a 2 cross 2 controllable and observable DCF form. Okay, so how it should look like? Okay, so x dot is equal to AX. Okay, A matrix means diagonal matrix because I am talking about DCF form. Diagonal matrix with distinct roots, distinct diagonal elements. Okay, plus BU and Y equal to CX. You want controllable and observable form. So controllable means here only 2 elements, but both should be non-zero. Okay, C also containing 2 columns, but both the columns should contain non-zero element. Correct? That's it. If you get such a B matrix, okay, the system is controllable. If you get such a C matrix, system is observable. Okay, system is observable. So have a look into another question before I go to the JCF. Have a look into this question, dear. A GATE 2016 2 marks question. A GATE 16 2 marks question. Have a look into this one. Okay, a second order linear time invariant system is described by the following state equations. Okay, let me write down the state equations in a simplified manner. D by dt of x1. Okay, that means derivative of x1. x1 dot is how much? Only derivative place on the right side. So this becomes minus 2x1 plus 3 into u. Then second equation, derivative of x2. How much? x2 dot is how much? Minus of x2 plus of u. Minus of x2 plus of u. Okay, minus x2 plus of u. Correct? Okay, this is what is the equations given. Now let's arrange it in the matrix format also. See, let me rewrite this equation. x1 dot is minus 2x1 plus 3u and x2 dot is equal to minus x2 plus u. Also, what is the output equation? Output C, or let me simply call the output as we normally call as y. So y equal to only x1. Y equal to only x1. So converting this in the matrix form, dear. What is the x dot? Okay, x dot is ax plus bu. Okay, now first equation only x1. So x1 coefficient minus 2, x2 is absent. Second equation there is no x1 but x2 coefficient minus 1. Then input coefficient, first equation 3u, second equation 1 into u. Okay, and output also. Output equation also. What is the output equation? Y equal to cx. Okay, which state variable? Only x1 coming, no x2. So 1 and 0. The coefficient of x2 is 0. Clear? Now look into this matrix. Okay, isn't it a DCF matrix? Because it is a diagonal matrix. Because it is a diagonal matrix, and that too with distinct roots, distinct poles, distinct eigenvalues. Yes, so it is DCF form. Now look into the B matrix. Okay, both elements are non-zero, controllable. That is what I told you, na? I've just told you earlier. And this one, okay, this entry is 0. That means it is not observable because you wanted all non-zero entries. It is controllable and not observable. It is controllable and not observable. Option number D. Very easy to answer these questions by Gilbert's test. If you apply Kalman's, you can apply Kalman's also. That will take little bit more time. Third order, so it will take much more time. But even in second order, for normal forms, Kalman's will take some time. Okay, well, Gilbert's is just an observation. You write down the matrix structure. Anyways, for Kalman's also, you need the matrices ABC to solve. If you write in the matrix structure, it is just 5 seconds ahead. Observe and say whether it is controllable and observable or both or none. Right, dear? Okay. Now, see, this was a GATE question, 2 marks. Now, let me come to the JCF form also. Okay, JCF form I explained you. Okay, now what is the Gilbert's test for the JCF form? What is the Gilbert's test for the JCF form? Controllability. First, understand controllability. Entire row of a B matrix that corresponds to last row of a Jordan block should not have all 0 elements. Now, what is this Jordan block? I will explain you with a question. Okay, let's understand controllability first. Have a look into this matrix first of all. Have a look into the A matrix, dear. What type of A matrix you have? Okay, the A matrix, is it upper triangular? Yes, you have a upper triangular A matrix. Okay, upper triangular A matrix. You have a upper triangular A matrix with what type of poles? You have a upper triangular A matrix with what type of poles? Okay, with repeated poles. Okay, upper triangular matrix with repeated poles. Okay, with repeated poles, correct? Okay, upper triangular, okay, with repeated eigenvalues. So see, DCF, I told you two things. If you have to identify DCF, A should be diagonal matrix with distinct diagonal elements. Okay, distinct eigenvalues. Number two, if you have to identify JCF, it should be upper triangular matrix with repeated, okay, with repeated eigenvalues, repeated diagonal elements. Okay, they should not be distinct now. So yes, there is one repetition at least. Okay, this is a JCF form. So upper triangular matrix with repeated eigenvalue corresponds to the JCF form. And now let's understand the Gilbert's test for JCF form. Let us understand the Gilbert's test for JCF form. Have a look into first only controllability. Now dear, I told you that in the Gilbert's test, we need to identify Jordan block, entire row of V matrix corresponding to last row of a Jordan block. Last row of a Jordan block. Now see, what is a Jordan block? One Jordan block is a block. One Jordan block is a block containing, okay, one particular eigenvalue. Now suppose, how many eigenvalues or how many poles are there? Okay, if I talk about the poles of system or eigenvalues of the system, okay, which are equal to the diagonal elements, because again it is a upper triangular matrix. So what are the eigenvalues? -3, and 1. This is what is repeated. Okay. So how many eigenvalues? If I talk about unique eigenvalues, there are only two, -3 and 1. So one Jordan block contains one particular eigenvalue. So one Jordan block will contain the eigenvalue -3, but because it is repeated, okay, because it is repeated. So because it is repeated, see here, this is one Jordan block containing one eigenvalue. Because it is repeated, so that will be known as a 2 cross 2 Jordan block. 2 cross 2 Jordan block. What is the next eigenvalue? The next eigenvalue is 1. The next eigenvalue is 1. It is repeated only one time. It is coming only one time. So it will have a 1 cross 1 Jordan block. This one. This will be my second Jordan block. How many Jordan blocks? How many unique eigenvalues you have? Only 2 unique eigenvalues. Only 2 unique eigenvalues. Right? Only 2 unique eigenvalues. Right? Okay, so J2, okay, is 1 cross 1. 2 Jordan blocks. Second one contains the eigenvalue 1. Okay, this eigenvalue is coming only once. So 1 cross 1 Jordan block. This is what is Jordan block. Okay, now let's go to the Gilbert's test. Entire row of B matrix corresponding to last row of Jordan block should not have all 0 elements. Okay, corresponding to last row of Jordan block. So what I am teaching, what I am covering on this slide is only controllability. Next I will take observability. And then I will give you the conclusion. So what is the last row of the Jordan block? See, there are 2 Jordan blocks. Come to J1. Now what is the last row of J1? Okay, it has 2 rows and this is the last row of J1. Okay, overall which row? This last row of J1 is overall second row, na? So go to the second row of B. See, overall, see, you have to consider last row of a Jordan block. Now I take J1. Last row of J1 is overall which row? Overall in the matrix, it is second row. So go to the second row of B. Okay, whether it is 0 or non-zero, okay, it is a row of 0. Here itself answer concluded, the system is uncontrollable. Uncontrollable. If this was non-zero, then we check next. Here it is not required, but let me check it for you. If this was non-zero, we go to the next Jordan block, which is 1 cross 1. What is the last row? So it has only one row. So what is the last row of this Jordan block? The last row of this Jordan block is overall which row? The last row of this Jordan block here is overall 1, 2, 3, overall third row. And since it is overall third row, I go to the third row of the B matrix. Okay, and which is again, this is non-zero actually. This is NZR. Okay, but still, even if one ROZ, uncontrollable. Uncontrollable. Okay. Similarly, let us go and understand observability, and then I place the comments. Okay, then I place the comments. Okay, suppose if you wanted controllable form. Okay, before I tell you observability, understand this. If you wanted a 3x3 controllable JCF form, then what are the elements you should see? JCF x dot equal to AX minus P1 minus P1 minus P2 repeated, and above the repeated pole 1. So that makes the matrix also upper triangular. This is the JCFA matrix. X dot equal to AX plus BU, Y equal to CX. Right now I have just told you controllability test, and as per the controllability test, okay, what was the problem? Okay, this went 0, so uncontrollable. If this was non-zero, then controllable. Okay, that means what will not matter here is the first element. What will not matter here is the first element. Clear? So what can I say? First element, okay, maybe anything. But if the second row contains non-zero, if the third row contains non-zero, and if such a matrix is seen in front of you, you can say the system is controllable. You can say that the system is controllable, correct? You can then clearly say that the system is controllable. Okay, fine. Now let us come to observability. Let us come to observability and conclude the observability rule as well. Observability. Have a look into this, dear. Have a look into this. Okay, firstly, again, let me make the Jordan block. So I already told you there are two Jordan blocks. This is known as the J1 Jordan block, which is 2 cross 2. Because -3 is repeated twice, so 2 cross 2 Jordan block will come. Next eigenvalue 1 is only coming once. Okay, so J2 is 1 cross 1. Now, Jordan blocks I have made again. Now let us come to the observability test. This is done, controllability. Now observability test. What is the observability test? For observability, again we will go to columns of C. But which columns? Entire column of C matrix corresponding to first row of a Jordan block. Corresponding to first row of a Jordan block should not have all 0 elements. So which columns of C? Columns of C corresponding to first row of a Jordan block. Okay, dear? Okay, what is this? This is the J1. What is the first row of J1? This is the first row of J1. Now again you have to see. The first row of J1 is overall which row? The first row of J1 is overall which row? It is overall first row. It is overall the first row. And correspondingly we go to the first column. Correspondingly we go to the first column of C. And what do I see? It is NZC, non-zero column. Same short forms I am using. Okay, fine. Then I will go to the second Jordan block. I have to confirm this for every Jordan block. This is second Jordan block. What is the first row? It has only one row and one column. What is the first row? This is only the first row. Overall, this is the first row of J2. Overall, it is the third row. And because it is overall the third row, I will go to the third column. Okay. I will see the entries in the third column, and that is again NZC. Both are NZC, so this time system is observable. That means what will not matter here in the DCF observability, this central element will not matter. This central element will not matter. So dear, in general, if I have to write down the observable JCF form, okay, observable JCF form, okay, here this first and third should be non-zero columns. Second could be anything, so I leave it as question mark. Okay, so if you see in this kind, the system will be observable also. If you see it in this form, then the system is observable also. If you see it in this format, the system is observable also. Okay, observable also. Done, dear? This is what it is. This is what it is. Okay. Let me also generalize similarly 2 cross 2. Okay. If you direct get a 2 cross 2 question, what is a 2 cross 2? Controllable. Controllable as well as observable JCF form. Okay, let me write it down for you. So JCF. Now JCF needs repeated poles. So minus P1, no P2, minus P1, and above the repeated pole, okay, we write down 1. So it is now upper triangular matrix. X dot equal to AX plus BU and Y equal to the CX. Okay, Y equal to the CX. Okay, now what I want? Okay, only one Jordan block will be constructed here. This is J1. Okay, last row will correspond to the second row, overall second row. That means second element here. This second element should be non-zero. First could be anything. Okay, then for observability, again we have only one Jordan block because only one eigenvalue minus P1 which is repeated. Okay, first row, overall first row, so we have to come to the first column of C, and this first column should contain non-zero. Second could be anything. Okay, second could be anything. Okay, so this will conclude controllability, and this type of C matrix will conclude observability. Okay, dear. Next question for you. 3 cross 3 JCF. See, dear, once again. Upper triangular matrix? Yes. Repeated poles? Yes. So JCF. That confirms JCF. That confirms JCF. Okay. Now, again, I'll tell you. For 3 cross 3 JCF, these are 2 marks question, dear. Okay. First element doesn't matter. Second and third non-zero, it should be controllable. In the C matrix, first and third non-zero, it is observable. Whatever is the second doesn't matter. Only on this observable, only on this observation. See here, second and third non-zero. Very good. Very good. It is controllable. First does not matter. Okay. And here, second does not matter, but first and third, yes, it is observable. Okay. Second and third non-zero, it is controllable. In the C matrix, first and third element non-zero, it is observable. Second doesn't matter. Finish. Finish. Controllable and observable both. Answer is option number A. It is finished. Okay. A GATE 2 marks question. GATE 14 2 marks question. Finish it quickly. You just need few seconds to solve this problem actually. Okay. You just need a few seconds to solve this particular problem. Have a look into this and please answer me. Right, let's do it. Let's do it, dear. First of all, my observation. Okay, what type of matrix? Okay, minus 1, 1, 0, etc., etc. It is upper triangular. Elements below the diagonal are 0. All elements are in the upper triangular. Upper triangular with repeated roots? Yes, it confirms JCF for me. Okay, now because it is JCF, I will go to the B matrix and see that this is 0. Okay, I want second and third element non-zero. It is 0, so it is not controllable. Finished. Okay, not controllable. Finished. For the C matrix, I will go to only first and third. Second not required. First and third non-zero confirms observability. It is not controllable but observable. It is not controllable but observable. Option number B. Gilbert's test. Okay, a big time, valuable method for you, especially for DCF and JCF, because Kalman's will be taking a lot of time for you. Okay. Right, Charan Raj, correct answer B. Kalman's is definitely going to take a lot of time here. Kalman's is definitely taking a lot of time here. That is how it is. That is how it is. Okay. Right. Now, dear, this was the 2 cross 2 DCF question which was done. This was also 2 marks, but very easy. Take this next question. Take this next question and see what is to be done here. Okay. Consider the system d by dt of xt equal to ax plus bu with a equal to 1001 and b equal to pq. Okay. And the question is only talking about controllability. That is why only B matrix given. We need the C matrix for observability analysis. For controllability, only B matrix is enough. Okay. Now, dear, x dot equal to ax plus bu. Understand very carefully. If I take the matrix A 1 0 0 1, what type of matrix? What type of matrix? See, This is a question I know many students I have seen committing mistake. That is why taking it specially. Okay, what is this? It is a diagonal matrix, no doubt. Okay, so is it DCF? It is a diagonal matrix. Okay, but with repeated eigenvalue, with repeated diagonal element. Okay, now tell me, is it DCF? What I told you for DCF, dear? What I told you for DCF very clearly? DCF means a diagonal matrix, but with distinct eigenvalues, non-repeated eigenvalues. Okay, so it is not DCF. Is it JCF? No, because JCF first of all needs upper triangular matrix. Okay, so because it is diagonal matrix, it cannot be JCF. And because it is repeated eigenvalue, it cannot be DCF. Okay, that means overall I can say that this particular form is neither DCF nor JCF. Tricks handled with care are only beneficial for you. And very clearly, whenever I took the DCF and JCF, I was clearly telling you what is DCF, what is JCF, how to identify. Okay, many students I have seen, okay, it is a diagonal matrix and diagonal means DCF, apply the Gilbert's test and you will get a wrong answer. Because if it was diagonal, then what you need as per the Gilbert's test, P and Q non-zero, and you will say that, okay, system is completely state controllable for non-zero values of P and Q. Now let us see, is it the correct answer? If you apply Gilbert's, it is A, but why can we apply Gilbert's? Gilbert's is only for normal form, either DCF or JCF. Okay, so remember, what is DCF, what is JCF? That true identity, that true identification you need to have. Okay, so what you need to do, if it is neither DCF nor JCF, okay, you cannot apply the Gilbert's test here. Okay, then this question is actually a Kalman's test question. This is actually a Kalman's test question. And we only need controllability? No problem. Okay, what is the Kalman's controllability test? Okay, what is the Kalman's controllability matrix? The matrix B and AB. It is a second order system, na? Okay, B matrix is given to me, P and Q. Okay, what is the AB matrix? So A matrix here is 1, 0, 0, 1, which is actually identity matrix, and that is why if you multiply by B, you will get back the same result, B only. Okay, so let me write down the B here. B is PQ. What is AB is PQ. What is the determinant of this matrix? Determinant is PQ minus PQ. Okay, 0. Okay, determinant is always 0 for any value of PQ. PQ minus PQ is always 0, na? Okay, so it is uncontrollable. Uncontrollable for what values of PQ? Any value, because PQ minus PQ is always 0. It is always uncontrollable. So that is why A is wrong, dear. If you apply Gilbert's, you say A and you get negative marks. It's an MCQ question. The correct answer is option number C. The system is uncontrollable. Uncontrollable for all values of P and Q. It is a Kalman's test question actually. Again, I repeat, if you missed the Kalman's test, what I am doing here, if you missed the Kalman's test, you can go and watch the previous session. That will make your controllability and observability finished. Okay, see, either alone first session or either alone second session. May be beneficial, but not 100% beneficial. Yeah, if you are preparing a topic, prepare it fully. At least controllability, observability will be 100% covered if you watch the previous session and this one also. What about this question, dear? What about this question? The second order dynamic system is given to you. D by dt of x is equal to px plus q, like ax plus bu. Here the matrix is P and Q. P is just like the A matrix. Now see, dear, what type of matrix once again? Kalman's is applicable for all type. That is the most generic test for controllability and observability. Okay, again, now you have an upper triangular matrix. Upper triangular matrix. Okay, you have an upper triangular matrix. Okay, let me actually write it here. The matrix A or the matrix P, here is an upper triangular matrix. Upper triangular matrix, correct? It is not diagonal this time. Okay, and with what type of roots? Okay, -1 and -3. Okay, with distinct, non-repeated Okay, with distinct eigenvalues. Now tell me what type of form it is and what test to be applied. See, upper triangular. Upper triangular means 100%. Upper triangular means it is not DCF at least, because DCF needs diagonal matrix. So it may be JCF, but JCF needs the upper triangular matrix with some repeated eigenvalue. At least one eigenvalue should be repeated. But here two eigenvalues, both are distinct. Distinct eigenvalues, all distinct eigenvalues. With all distinct eigenvalues, it cannot be JCF also. So again, okay, it is neither DCF nor JCF. Okay, so you have to solve it by Kalman's test only. And Kalman's test we covered with questions in the last session, so I will give this one as a homework for you. This is again to be solved by Kalman's, and you solve it and you have to complete it as homework. So remember guys, only diagonal matrix, like the previous question, only diagonal matrix doesn't confirm DCF. Similarly, this question, only upper triangular matrix doesn't confirm JCF. You have to be very clear, I repeat. Okay, diagonal matrix with distinct eigenvalues is DCF. Upper triangular matrix with some repeated eigenvalue is JCF. Then you can apply Gilbert's test, otherwise you commit mistake. So this is again not on Gilbert's test. This is Kalman's test, which was covered in last session. This is a homework for you further. This is a homework for you further. Right, dear? Alright guys, once again a quick reminder that, okay, on 12th of January 2025, okay, the OM Institute brings to you the All India Open Free Mega Mock Test. Feel the gate before the gate exam. True feeling of gate before the gate examination. Real-time experience with All India ranking and detailed explanation for all our questions, and special exciting gifts for the toppers, for top 5 students, for top 5 performance. Okay, what you have to do, the registration is free, the test is also free. In fact, appearing in the test is also free. The test is for EC and EE both. Okay, what you have to do to register, you just scan the QR code. For your convenience, I have put up this QR code here. You just scan it. It will take only few seconds to register, and yeah, your task will be done. Okay, any queries, you can contact 95156 94053. And one more big time, announcement. As you all know that GATE 2025 online live crash course, okay, to cover up the entire syllabus, okay, in a crash course, fast track manner, in a complete 2 months. Okay. The validity will be 4 months. That means you can even watch the crash course after the GATE exam if you are preparing for some other government exams or etc. The fee is 5499. For any previous OM student, 3499, and for current this year OM students enrolled in any batch, offline or online, 2499. Okay, right. The GATE 2026 big announcement. Okay, the first offline regular batch for GATE 2026 on February 24th. Okay, for February. Starts on February 24th. Okay, the fee 65,999 is currently placed as 54,999, and if you register till 30th Jan, you get an additional 4,000 discount. You get an additional 4,000 discount. Okay, and of course some special discounts for special college category students that you can see here. All right, guys. If you can't if you can travel to Hyderabad, you are most welcome. You enjoy and learn under the direct supervision of faculty. The beauty of the offline manner. Okay, but in case if you want to still study by the same experienced, same faculty, getting same type of content, but you can't by chance come to Hyderabad, so then the GATE 2026 or 27 online live batch is also there for you. Okay, the fee for GATE 26 currently is 19,999, validity 12 months. For GATE 27, the fee is 29,999 for validity of 12 months. The platform will be OM Live app. Okay, guys, if you are preparing for Telangana AE exams, okay, so the next batch for Telangana AE exams, okay, AE offline batch starts on December 26th. Okay, that is just tomorrow. Okay, AE offline batch, right? If you are preparing, if you want, the pre-recorded courses, online pre-recorded courses, that is also available for AE. Okay, so online pre-recorded lecture course, validity 9 months, 20,999 is the fee. Okay, for validity 3 months, 10,999. Okay, for AEE electrical examination, 3 months validity, 12,999 will be the fee. Okay, and for 6 months, again AEE course, 18,999. Okay, this is, I think I already mentioned. This is repeated. Okay, yes guys, that's it from my side. Okay, hope you enjoyed and hope you are concepts of controllability and observability are cleared. Okay, many more sessions to come up, and don't worry, the entire marathon revision sessions, okay, by all the faculties will be going to come up on the OM YouTube channel. So stay subscribed. If you are not subscribed, hit the subscribe button right now so that you are all notified when the marathons will going to come, when are some more champion series session going to come up, etc, etc, etc. Okay, this is Rakesh Talreja signing off. Okay, I will share you this PDF. Okay, this PDF and yesterday's the Kalman's test, both the PDFs I will share in Telegram. Okay, but as my rule, always the PDFs are password protected. Okay, so what is the password? Simple password, test. We have learned two tests, Gilbert's test and Kalman's test. The PDF will be password protected, a simple password, everything in small letters, TEST. Everything in small letter, TEST. Okay, you will get it in this Telegram group. All right, dear, bye-bye. Thank you. Good night. Stay safe and do take care of yourself.